Hey everybody. Today we're going to start looking at how to produce a fully 3D printed working water pump. It's actually this one right here, this pump here. And there are several parts to it. We'll go into each one of those parts in this series of videos on how to design it and build it from scratch. Just to give you an idea of what the 3D model looks like. So this one is the 3D model as made in Fusion 360, and then to the right of that is the finite element analysis of the same model. As we walk through this, we want to see how it performs both in actual pumping efficacy as well as how it will most likely fail. So that rainbow colored image that you're looking at to the right is the results of a simple finite element analysis. And if you look, there's a small little red spot right on the underside of the handle where it makes a connection. That's predicting the failure point of, in this case, the water pump. Well, it just so happens that we produced one of those pumps and brought it to failure. And as you can see, the FEA analysis is spot on in showing exactly where it failed, right there at the connection point. There's the piston. So we're going to walk through all these things as we work towards understanding the design choices behind making this water pump, the actual design process, and then finally getting it ready for 3D print and finite element analysis. So to start understanding how this pump works, we want to look at the full model and specifically the two valves that are embedded into this model. So if I use an analysis plane to slice it open and we can look inside, you'll see in this model there is the mechanism that we are all familiar with, which goes up and down, the rocker slider mechanism, like so. And then there are two check valves embedded in here. Right? So you've got the piston head here, which has a form of check valve. And then down at the very bottom, there's this add-on cap that I designed in to also have a secondary check valve. So that brings up the question, what really is a check valve? And when I say check valve, all I'm referring to is a physical mechanism that allows water to flow in one direction and not in another. Right? It checks the flow. So water can go through a pipe in one direction, but it cannot go backwards. Now, if we look at this bottom check valve, we accomplish checking the flow into one direction by simple means of having an optional seal, right? Depending on where this cap will flow. So when this cap is floating in here, water is free to push it around. Right? So if I've got that structure that looks like this for the side walls, and then I've got the floating cap in here, when water is pushing this direction against the cap, it will push the cap into contact with this sidewall, right? Thereby sealing it off so that no water can get through there. That makes sense? Now, in the other direction, so water can't flow down. It's stopped by that cap. In the other direction, when water is pressing against that cap there, we'll draw it over here on the side very quickly and poorly. When water is flowing in this direction, it'll actually push the cap further up, like so, and water is allowed to flow around the side of that cap. So, with just having a little shaped cap like that covering the channel, you allow water to flow one direction and not the other direction. One thing we have to add necessarily when we're doing this sort of a check valve design is a capture mechanism. Right? So with the current design that we have, you've got these sidewalls that contain a chamfer in them, and then you've got a cap that sits in there that makes a seal in this area here. depending on whether the water is flowing up or flowing down. If the water is flowing up, however, and this cap is free to move, it will get flushed completely out of the channel unless we add some sort of retention element, right? A little stub of plastic or a design feature that will prevent it from flowing all the way out. Now, if we look at the cap design in Fusion, we've done just that. We have these little nubs here that prevent it from flowing. So if I turn on contact, I can show you this will move up only that far, and it'll move down to create a seal, and it'll move up only that far when it hits those little buttress elements, and it is prevented from going any further. Additionally, I added some other things to this check valve mechanism. To increase flow rate, I added these little notchaways here. That also enables the cap to stay in proper alignment because these buttresses will fit into those grooves. And then lastly, I added, well, the buttresses themselves, if you notice, these are not flat horizontally. They are angled at a 45 degree. I do that specifically because those buttresses are going to be 3D printed, right? Again, the entire goal of this model is to be 3D printed, and if we print from the bottom up, for instance, here's our wall, right? And the printer creates the bottommost layer first, and then moves its way up, creating layer by layer, as you can see like this. If we were to try and print just a simple overhang like this, there'd be a problem, right? We are printing this plastic where there's nothing below it to support it. So one easy way around that, if you're designing for 3D printing, is to add a 45-degree chamfer like this to whatever the design feature it is that you're making, and then it can grow the part horizontally as it moves up. Now, I should say, you can add chamfers like this to a 3D design if it doesn't impact the way that your design functions negatively. Right? In this case, I actually added some other features that correspond to the vertical growth or horizontal growth of this buttress to take advantage of it. But as long as this added 45 doesn't impact negatively the rest of the performance, you can go with it.